Hi, I'm Alex Shelley. I'm a current ARC scholar studying at Stanford. A little bit of background about me. I was born in Virginia, but when I was in second grade, I was diagnosed with a rare autoimmune condition, which forced me out of school. Eventually, our family packed up and moved to San Diego so that I wouldn't be around my severe allergy to tree pollen. I lived right next to UCSD, and I was eventually befriended and mentored by a physics professor there, Fred Driscoll. And while I was still too sick to attend regular school, he would come over to my house to give me physics lessons. And with his help, I was actually eventually admitted to UC Berkeley to study when I was 14 years old. There, I double majored in physics and math. And then after graduation, I came to Stanford, where I am now a third year applied physics PhD student. And I'm studying under Daniel Tartakovsky. So my research focuses on solving differential equations for physics, which describe the flow of how things like water or smoke move around, like the flow from this candle. And I'm specifically interested in the Schrodinger equation, which tells us how quantum mechanically electrons move around. And quantum mechanics tells us that electrons really behave more like the smoke on the left than a baseball or a particle, shown on the right, for example. So many of the materials that we really care about, like metals, insulators, semiconductors, have a crystal lattice structure, like the salt crystal shown here. And this periodic, regular grid of molecules affect how the electrons can flow through the material. And actually, most of the physics that we understand about solids is a direct consequence of this crystal structure. The crystal lattice makes the electron fluid granular, like sand. Zoomed out, sand flows like water. But zoom in, and you notice it behaves very differently because it comes in discrete chunks. I zoomed in on electron flow on a lattice, and I discovered a very surprising effect. What I found is that if you put two electrons next to each other on a lattice and then let them go, they will actually be stuck to one another. This is very surprising because classically you expect electrons to repel. And in fact, what I found is that the stronger that the electrons repelled one another, the more stuck together they would be. A numerical simulation of this effect is shown in this plot, where the y-axis is the distance of each electron to the other, and the x-axis is time. The different plots show different repulsion strength, and we see that the stronger the electrons repel, the more tightly they are stuck together. This effect, which I call the potential inversion theorem, turns out to be quite general, and is the subject of the paper of the same name which I've now submitted for review. Finally, I'd like to say that none of this research would have been possible without the generous donation and fellowship from the ARCS Foundation, so thank you.